Welcome to another lecture video on junction field effect transistor. In this video, we will look into the water tap analogy in case of JFET, the working principles of JFET when a positive potential or voltage is applied between the drain terminal and the source terminal when the voltage between gate and source is 0. We will talk about the effect on the depletion region, and finally we shall look into the symbol of junction field effect transistor. Let us first look into the water analogy for the JFET control mechanism. Here we can see a picture of a water tap or a spigot. This is the water tap. Here we see its knob. Here is the sink. Let us say that the knob represents the gate terminal, the sink represents the drain terminal, and the tap as a whole represents the source terminal. The tap is connected to an overhead water tank. The water is coming from the water tank to the water tap. Now, the water flow is happening because of a potential difference. In the potential difference here means, of course, the water level at the water tank. Now, the flow of water is controlled by this particular knob. By moving this knob, we can increase or decrease the water flow level. So gate terminal, here if we say this knob is the gate terminal, it controls the flow of water level. Similarly, we have seen that the gate terminal in case of JFET can control the flow of electrons by changing the width of the depletion region. The sink here is the drain terminal. As we can see, if we apply a positive potential difference, which we will elaborate in this particular video also, then there will be flow of electrons from the source terminal to the drain terminal. This flow of electrons in case of this water tap is nothing but water flow. So water is flowing here from the source terminal to the drain terminal. So drain here is nothing but the sink, source is the water tap, and the knob here is the gate terminal. Let us now look into the working principle of JFET. In this scenario, a positive potential is applied to the drain terminal. The source terminal is grounded. So in between the drain terminal and the source terminal, we have a voltage or potential difference above 0 volt. The gate and the source terminal are connected together and then it is grounded. So the voltage difference between gate and source terminal is 0 volt. What happens in this situation? As we can see, the drain terminal has a positive potential. Therefore, the electrons in the N channel, which are the majority charge carriers, will be attracted towards the drain terminal. As we can see, the drift of electrons towards the drain terminal. Now the conventional current flow is in the opposite direction of the electron flow. So this indicates therefore the conventional current flow of the drain current. Now let us look into the shape of the depletion region. Earlier, when no potential was applied across the terminals, the width of the depletion region was uniform. Now we can see it is not so. The width of the depletion region is more towards the drain region and it is much lesser towards the source terminal. Why is it so? We will explain that in the next slide. Let us now we know already that the N channel provides resistance to the current flow. Let us consider the channel is made of 4 resistors connected in series. Here we can see 4 resistors all have equal value are connected in series. These represents the combined resistance of an N channel to the current flow. Now let's say the drain terminal is connected to a potential of 2 volt. So across this N channel there is a total potential difference of plus 2 volt. This 2 volt is divided equally across all these 4 resistances. So across one particular resistor there will be a potential difference of 0.5 volt, because all the resistors have same resistance. So at this point we have 1.5 volt. At this point the voltage will be 1 volt. At this particular point it will be 0.5 volt, and finally we will have 0 volt over here. So total potential difference across this channel is plus 2 volt. Now we know that the gate terminal is connected to ground, so the gate terminal has 0 voltage. So the voltage difference between gate terminal and at this point over here is nothing but 1.5 volt. This is reverse biased. So we can see, as we know, we have already discussed, if we increase the reverse bias voltage, the width of the depletion region will increase. Here the reverse bias voltage value is more compared to this region. Because the reverse bias voltage value is more over here, the width of depletion region will increase more over here compared to insignificant increase in this region. So this explains why towards the drain terminal the width of the depletion region increases more compared to the width of the depletion region towards the source terminal. Finally, let us look into the symbols of JFET. This shows the symbol of N-channel junction field effect transistor, or JFET. This is the symbol of P-channel JFET. Now how we are going to differentiate between these two symbols? How we are going to know which one is N-channel, which one is P-channel? Now as we have seen in case of NPN and PNP transistor, the direction of current flow differentiates these two symbols. In case of NPN BJT, we know the current flow is away from the base terminal. In case of PNP transistor, it is towards the base terminal. Similarly, in case of N-channel JFET, the current flow is towards the gate terminal. For P-channel JFET, it is away from the gate terminal. In this way, we can differentiate between the symbols of N-channel JFET and P-channel JFET. That's all for this particular lecture video. In the upcoming videos, we will continue working principles of JFET. Thank you for listening to this video.